Hi all. Today we're going to be talking about one of my favorite topics, solubility. I really enjoyed this topic for multiple reasons. One, because it relates to a number of things that we already probably know but might not actively think about. But it also has implications that extend into the realm of biochemistry and organic chemistry, and a lot of it really does a great job of explaining a lot of phenomena around us. So what we'll be doing is looking at three aspects of solubility. Basically, we're trying to seek to explain what will dissolve in what and how can we modulate that. We'll be looking at this thing called the like dissolves like principle. Then we'll be looking at how temperature affects solubility. And then finally, we'll talk about the solubility of gases in liquids. So to review the dissolution of a salt. Previously, we looked at electrolytes in solution, specifically salts and what they do in water. And basically what we had, if we throw a salt such as sodium chloride into water, the water has to overcome its intermolecular forces to kind of break apart. The solute needs to overcome its intermolecular forces. The ion-ion interactions come apart. But then the payoff is we get these ion dipole interactions. We get these new intermolecular forces formed between the solute and the solvent. That's basically the payoff step. So in the case of something like this, it's basically the water swarms around the ions and intercalates itself in between them. Swarm, swarm. So now a concept that we're probably already familiar with. If you've ever had a salad and used some sort of vinaigrette or an oil and vinegar dressing, you probably know that if you let it sit for a little while, it will phase separate. It will go into two different immiscible layers that aren't mingling. So do oil and water readily mix and dissolve in each other? No. No, they do not. So let's meet the main components of olive oil and of water/vinegar. So olive oil consists of, in some cases, up to 83% oleic acid. And these structures are just purely FYI. These are individual fatty acids. They're called fatty acids because they have, well, the acid part they get from the fact that they have a carboxylic acid in them. And fatty comes from the fact that they have these long hydrocarbon chains in them. So oleic acid is about, well, it can be up to 83% of the fatty acids found in olive oil. There's also linoleic acid and palmitic acid are pretty commonly found in olive oil, and palmitic acid, especially in butter. So just as a note, in living systems, these fatty acids generally dock themselves in this thing called a triglyceride. It's called that because, well, the glycer comes from the fact that there's this glycerol head. It's basically holding together these three chains. So tri comes from the fact that there's three fatty acids held together through this glycerol head group. So just in general, this is how usually these fats are found in animals and plants, etc. Now, let's meet the main component of water. Ah, yes, H2O. Excellent. So a really useful rule of thumb to determine what substances, what solvents and solutes will be miscible is this like dissolves like principle. What does it mean? Well, it means that if two substances share very similar intermolecular forces or primary intermolecular forces, they will more readily interact with each other. And so that in that last step, when we looked at with the solvation process, where there's these new interactions formed between solutes and solvents, if they share more intermolecular forces, there's more of a payoff in that step. And so they're more likely to dissolve in each other. So the gist of it is that small polar molecules are molecules that are larger but have lots and lots and lots of polar groups, and ions tend to dissolve very well in water. Water is great at swarming around, forming these dipole-dipole interactions, hydrogen bonds if you've got OHs or NHs in those molecules. And also, if you have ions, we saw those dipole ion interactions can form. Now, larger, less polar molecules, like for example, our fatty acids that just are like hydrocarbon city, population, oleic acid, those tend to dissolve better in organic solvents, large hydrocarbons or ethers. So now oil and vinegar, a closer, cartoonier look at what happens with these. When you look at oil, which has long hydrocarbon chains, and you look at water, very small polar molecules, they don't tend to mingle well. So they form these two layers. The oil is on top because the oil is less dense than the water. So the water has a greater density, goes to the bottom, and we get these two partitioned layers that mingle well within themselves, but not with each other. If we look at acetic acid, we've talked a little bit about acetic acid already. So acetic acid is what gives vinegar its punchy taste. It's a small polar molecule, so it interacts very readily with water. In general, vinegar is often about 5 or 6% acetic acid in terms of its by volume. And so here we have an image of acetic acid mingling well with waters, not so much with those large hydrocarbon chains. So now let's do a little gauntlet. We're gonna look at each of these, and I want you to tell me, will it be more soluble in water or in oil? So I'll pause dramatically after each one. So the first one is acetic acid, and go. Water, yes, it's small, it's very polar, hydrogen bond city, water's good. That next one is pentane. What do we think about pentane? Oil, more likely to dissolve in oil, triglycerides, hydrocarbons, etc. All right, up next, we have this amino acid here. It's a pretty small one, got a lot of polar groups. What do we think about that? Ah, yes, also more soluble in water, because there's a number of interactions available for like hydrogen bonding. Look, OH, NH, OH, all over the place. So it's still a pretty small molecule, and it's very polar. Finally, we have sodium chloride. Once again, water. Water is great at intercalating itself in between the ions. Okay, so now presenting demonstration station, kitchen chemistry. Oil, water, and blue food coloring. Let's see how these things mingle or don't.
Live from my kitchen. Well, not really, pre-recorded from my kitchen. So, what we're going to do to show this principle is, we have olive oil. We have the molecules in here. We have these triglycerides that consist largely of long hydrocarbon chains. And we have water in this cool, nifty beaker. So I'm going to pour the two of them together into this vessel. So I'll pour in water, pour in the oil, this long hydrocarbon chains. And do they seem to be interacting readily with each other? Well, no. They're forming these immiscible layers. And just to kind of make this a little bit cooler, so I have here a blue food dye. Next week we'll talk about the like dissolves like principle. But this particular blue food dye happens to have a lot of OHs in it. So it interacts readily with water, not so much with hydrocarbon chains. I'm going to put some in here, and notice that it's not really mingling. It's forming these droplets, not so much dissolving. Now there's some surface tension down here, the oil and water. Once we break that interface, promise this is going to look really, really cool. It's breaking. Once we break that interface, we're going to have it entering the water. Break. Break. Break the interface. Now that's in the water. Turns out that this dye is quite soluble in the water. So I'm going to give this a nice shake. It's dissolving readily in the water. And I might have shaken it too much.
Why is it that it mingles so well with water like we saw? Well, even though it is a, sort of largish molecule, look at all of these OH groups here. These can all form dipole-dipole interactions with water. Moreover, we also have these polar groups that are in here. It just forms a very favorable set of interactions with water. So this phenomenon also explains water-soluble vitamins versus fat-soluble vitamins. If we look at the water-soluble vitamins, what are their commonalities? Well, they all have a vast abundance of these polar groups in them. Vitamin C, vitamin Bs. Vitamin B12 is a very large molecule, but look, it's like polarity city, population, vitamin B12. So as a result, these tend to dissolve well in aqueous solutions. So you can find them pretty readily in juices. Oftentimes, if you look at, say, orange juice, which is mostly water, you'll find a lot of vitamin C and B vitamins, etc. Now, instead, if we look at the fat-soluble, the lipid-soluble vitamins, things like vitamin A, D, E, and K, these ones, they do have some polar character to them, but they have a vast amount of carbons and hydrogens. They're largely non-polar molecules. So as a result, they don't interact that well with water. It's harder to fortify aqueous solutions with these sort of vitamins. However, something that has fats and proteins that can dissolve them, like milk, for example, you can find them more readily in. And now presenting the tragedy at the Bollesburg Zoo. So buckle your safety belts. This is a bit of a ride. So recently at the Bollesburg Zoo, don't know if you've ever been to the Bollesburg Zoo, pretty impressive actually. Some pretty decent large mammal exhibits. And recently they acquired this bear. And bears have to have a pretty large enclosure. Cave, a little forested area, nice little water feature. Well, they recently got this bear, and the bear went over to the water feature to presumably get a drink of water, and went up to the water, just dissolved right into the water. Do you have any idea why the bear dissolved into the water? It was a polar bear. Like dissolves like. And yes, there was an entire slide dedicated to this joke. There's not really a Bollesburg Zoo, not to my knowledge at least. So some really cool applications of this principle, biological membranes. So biological membranes consist of, these fat motifs, they actually are found in what surrounds our cells. And so we have these things called phospholipids that have one side that's really polar. It's got charges on it. It likes mingling with water. Then we have these large hydrocarbon chains that, not so much. So we can divide them into two ends. One side we say is hydrophilic, literally means water loving, loves to interact with water. The other side we call hydrophobic, literally means afraid of water, wants to get away from H2O. So rather than drawing out these large structures every time we want to represent these, we can use these cartoons where we have a circle representing the polar side, the charged side, the polar head, and then we have these squiggles that represent the nonpolar tails. So this principle actually tells us why membranes form spontaneously. Let's take a look. So given what you know about the like dissolves like principle, let's just take a quick moment and see if you can predict which of these motifs are prevalent in biology. So we're assuming that water's on the outside of these and that we just want to see how they're going to interact. So take a moment and see if you can predict which of these are common biological motifs of these phospholipids. And go. And let's resume. The answer is 1 and 3. So let's take a look at sort of what happens at this really high-tech animation as to what goes on when making a membrane, like what goes around a cell. So these will spontaneously organize themselves so that there we go. So that the polar head groups are able to interact more with water. So they'll tend to go on the outside, facing an aqueous interface. On the other hand, we have these lipid tails that don't want to interact with water. So they'll burrow onto the inside. They'll interact with each other readily, and not so much with water. So we end up getting some really cool motifs out of this. Here are some examples of them. So we have liposomes. Liposomes transport fats and drugs throughout the body. We have this lipid bilayer that's going around, kind of a smaller sort of collection here. We have micelles. Micelles don't have what's called a bilayer. They have one layer of these polar head groups going around them, but they form basically this sphere where you've got the polar head groups on the outside and the hydrophobic tails on the inside. Then we have these things called bilayer sheets. This is what surrounds our cells. So you've got water on the outside, you've got water on the inside, and then the hydrophobic tails are being protected. They're basically burrowed in and they're shielded from the water by the hydrophilic groups. So these are some really important motifs for people in the life sciences. Also, and this is just purely FYI, but I think it's really, really fascinating. The whole idea of why proteins fold to the specific shapes they do. Proteins are amazing molecules. They consist of these monomeric units that bond together, and you can have thousands upon thousands of atoms in a single protein. Now, some of these monomers, some of these small individual units that come together have very, very polar functional groups attached to them. Those ones want to interact with water. Some of them have just large hydrocarbon chains. They're not so much. So the way that proteins fold, they've got this primary structure that's just basically like the transcript, the amino acids combined together, tells us what they are. The secondary structure is oftentimes formed by hydrogen bonding interactions. And we get these two really prevalent motifs. We have these alpha helices and beta sheets. Finally, the tertiary structure describes the three-dimensional shape of a protein, and it's largely dictated by this like dissolves like principle. So all of these amino acids have an amino, and a carboxylic acid. Acid, classic. What's different is the functional group that's attached to them. So in some cases, they're just carbon and hydrogen. Those ones tend to be hydrophobic. They want to burrow into the inside of a protein. They don't want to interact with the water outside of it. Some of them are larger. They're even more hydrophobic, like for example, tryptophan here. Some of them are acidic. Some of them, so that one has, we can see on it a carboxylic acid. Some of them are basic. They have an amine on them. Some of them are very polar. Those ones want to interact with water. Some of them get a charge on them. Those ones love interacting with water. So basically, these proteins will fold such that the hydrophilic sides, the ones that want to interact with water, will be on the outside. They'll form this active site, more on that in a moment, that will be on the outside, and then the hydrophobic side will burrow itself into a core. And we get these really, really, really precise shapes, these remarkable shapes that form these pockets that very, very specifically hold on to very specific molecules or motifs. So we call this pocket that's built into an enzyme or a protein an active site. And it's basically kind of like a puzzle piece. So it's designed so it'll fit with very specific molecules. So for example, we call those molecules substrates. And what these do is they hold these molecules in very specific orientations to allow the facilitation of the reaction to go faster. Now you'll learn more about how fast reactions go and about enzymes and catalysis in Chem 112. But for right now, these principles that we're talking about have these really profound implications in real life. These molecules are massive and they form in very, very specific ways because of these interactions. It's just so cool. So here we have an example of glucose, C6H12O6. It's represented by that little disc here. So we have glucose here. And this pocket, this active site, very specifically binds with glucose. And look at how big that molecule is. It's massive. But because of these interactions, it's got that specific pocket to hold glucose like a puzzle piece and facilitate the reaction. It's so cool. Anyway, there's our active site. We call this, once they bind, the enzyme substrate complex. Again, this is out of the scope of Chem 110. It's just a really neat application that will be very important to many of you as you go through your academic career and, well, professional careers. So now let's talk about the dissolution process and ways that we can alter it. So we have our solute and solvent, and when they mingle with each other, we end up getting a solution. The key factors for solubility are intermolecular forces, the like dissolves like principle. That's what we've been talking about. Temperature also plays a big role. If you've ever put sugar into cold tea versus hot tea, this is something that you've witnessed firsthand. Then finally, we'll talk about gas solubility, and we'll see that the partial pressure of the gas has a lot to do with its solubility. So let's explore these concepts. This one, just to kind of re-emphasize what we've talked about before, the like dissolves like principle. Let's look at this specific molecule, ethanol. So what kind of molecule is C2H5OH? It's an alcohol. It's got that OH, polar OH group, able to form hydrogen bonds with water. What kind of intermolecular forces does it have? Well, it's got the trifecta. It's got LDS, it's got dipole-dipole available, and it's got hydrogen bonding available. Is it an electrolyte? No, it doesn't turn into like C2H5O minus an H plus in a solution. It stays together, but it still is miscible in water. And it turns out it's kind of like the perfect combination of a little bit of hydrocarbon character, a little bit of polar hydrogen bonding character to dissolve in both water and also cyclohexane, which cyclohexane is just a well, it's just carbon and hydrogen, C6H12. So that's cyclohexane. So depending on, so here we have a list that we have methanol, we have ethanol, we have propanol, we have butanol, we have pentanol, we have hexanol, we have heptanol. We have all these hydrocarbon chains that have an OH group on them. What do you notice is happening as the number of carbons and hydrogens is increasing? So all of these do have a polar group. But as we increase the number of carbons and hydrogens, we can see that, well, methanol, ethanol, and propanol, the first three listed, they all dissolve in water very readily. But then once we get to butanol, the one with 4 carbons, its solubility starts to go down starkly. And then as we add more and more carbons, it becomes increasingly less soluble. So why is that? Well, as we add in more and more carbons and hydrogens, at that point, the hydrocarbon character starts to take over. So the molecule becomes a lot less polar and resembles more a non-polar molecule. So this is a little bit of the like dissolves like principle in action. Likewise, if we look at solubility in cyclohexane, methanol doesn't have enough hydrocarbon character to be completely soluble in cyclohexane. But then once we add in more carbons, then there's enough carbons that can interact with their LDFs and dissolve readily. So we call this hydrocarbon character versus polar character as a way of describing this. Now then, an application that as a hot pepper enthusiast I particularly like is capsaicin. So capsaicin is what's responsible for giving hot peppers their heat. This is what causes the burning sensation when you eat, say, a habanero or a jalapeno or a hot sauce, etc. So think about this. If one's tongue is tingling after consuming a habanero or some hot sauce, which of these solvents do you think would work better? Water, H2O, or milk, a combination of some water in there, but then it's also got fats and proteins. So take a moment and contemplate it. And I'm going to do this demonstration IRL. Wish me luck. My tongue is about to be lit up. Welcome back to this edition of Things I Regret Before Doing Them. Hot sauce edition. So what I'm going to do is pour out an unreasonably large amount of this Cholula hot sauce. Quick description about this. The original flavorful fire. It's a delicious exclusive blend of red and Pequin peppers and signature spices. Excite the flavor in everything you eat. Okay, so I just did some research. The Pequin pepper actually has about 5 to 8 times hotter than a jalapeno on the Scoville heat unit scale. And what makes it really hot is the capsaicin content. So this is the molecule that we're just looking at. This is such a bad idea, but such a good hot sauce. Okay, so in the name of demonstrating the like dissolves like principle and how I'm going to heal my tongue after this. Here we have our hot sauce. Science! It's building. Yep. Oh, that's hot. All right. Not overly pleasant. Okay, what am I gonna do? Get a glass of water, okay? Nope, still there. So the water is giving a temporary reprieve from the heat. When it's in my mouth, it's feeling cooler, but then it's coming back. The water's not doing a good job at dissolving that capsaicin. Here I have chocolate milk. Let's try this instead. Yeah, okay. This is providing more of a long-lasting relief. So milk, because it has more fats, more proteins, and more hydrophobic molecules in it, or at least portions of hydrophobic molecules, it's better able to mingle with that capsaicin, able to dissolve it and whoosh it away. This isn't terrible, but I don't recommend doing it at home. I mean, you can. That wasn't a great idea. Although that chocolate milk is really good. Back to the lecture. Yowzas. Whew. Anyway, capsaicin, am I right? Now, let's get a little bit more quantitative here. Let's talk about solubility. Solubility tells us how much of a solute will dissolve. So the definition of it is the amount of a substance that dissolves in a given quantity of solvent at a given temperature to form a saturated solution. So saturated solution, what's that mean? Well, for example, water is pretty good at dissolving sodium chloride. If you have 100 milliliters of water and you pour in 30 grams of salt, all of it will dissolve. So we have this unsaturated solution. It hasn't reached its tipping point yet. If you try to put in 40 grams of sodium chloride, on the other hand, 4 of the grams are going to remain undissolved at particular time. I'm not sure what temperature this is at. Let's just say 25 degrees Celsius. Well, we have a graph where we can analyze it in a moment. Anyway, so at the same temperature, if you pour in 40 grams, 4 grams go undissolved. So that means that basically the capacity of this 100 milliliters of water is 36 grams of NaCl. Can dissolve it. Any more, forget about it. So at this particular temperature, 36 grams will dissolve for every 100 milliliters, or 0.1 liters. So we could say that the solubility is 360 grams of sodium chloride per liter of water here, okay? So, supersaturated, saturated, unsaturated. What's the deal with all of these? Usually we have this really cool demo where we have the supersaturated solution and we pour it and make this pillar of salt. I recommend YouTubing pillar of salt. It's a really neat demonstration. Anyway, the idea is saturation is basically a limit. It's a capacity for a given solvent to hold a solute. Once you reach that capacity, you can't put in more of a given solute. So a saturated solution has the maximum concentration of the solute that's allowed under the given conditions. It is, however, possible to make a supersaturated solution. And those of you that have made rock candy are familiar with supersaturated solutions. We form, well, the way that we do it, this is kind of a spoiler alert into the next slides, but we heat up water, we get it boiling, we pour in sugar. At really high temperatures, more sugar will dissolve. But then what we do is once we dissolve a lot of sugar into it, we cool it. And we get it to a temperature where it's got more sugar dissolved than it can actually technically handle. And it'll stay dissolved until you perturb the solution, say with a nucleation site or a seed crystal. At that point, you'll get this precipitate, you'll get a solid that crashes out of the solution. So a supersaturated solution is when the concentration of the solute is actually greater than what that solvent will allow under a particular given set of circumstances. And again, the way that we do that is through most often changing the temperature. So here we have graphs showing a lot of different solutes and their solubility in 100 grams of water. Make sure to pay attention to the y-axis here. So there's kind of a lot going on, but really the graph is pretty straightforward. It tells us that at any given temperature, which you can see on the x-axis, it tells us how much of the given solute will dissolve in 100 grams of water. So make sure that you can interpret this graph. And generally speaking, usually salts become more soluble in water as the temperature increases. There are some exceptions. We can see some of these actually slope downward. For the most part, these go up. And like if we look at glucose, glucose spikes rapidly as we increase the temperature. So that's why if you have cold tea, sugar, it probably won't dissolve that well. If you have hot tea, it'll dissolve really, really readily. So let's do a quick click. How many grams of glucose can you dissolve in 200 grams of water? Note the number at 20 degrees Celsius. Take a moment, pause the video, see if you can solve it. Go. You did it. The answer is 180. So notice here that the question asks, how much can you dissolve in 200 grams? So our y-axis here says the solubility in 100 grams. And we can see here, if we go to 20 degrees Celsius and we look up, you can dissolve about 90 grams or so of glucose in 100 grams of water at this temperature. If you have twice as much water, you can dissolve twice as much solute. So that's why the answer is 180. So then finally, gases. Gases, generally speaking, are not that soluble in water. And actually, kind of an interesting trend, it's kind of like the opposite of what we just saw. As you increase the temperature of the solvent, what do you notice is happening to the solubility of the gases? It decreases. Why is that? Well, gases, again, in general, aren't going to be that soluble in water. They're going to sort of be trying to escape that water. If you add in more heat, there's more kinetic energy. There's more energy for those gases to escape from the water. So think about soda on a cold day versus a hot day, or in the refrigerator versus sitting out on a hot day. And actually, I'll come back to this analogy in just a moment, but soda is a really good way of thinking about gas solubility. So the final thing that we want to discuss is this thing called Henry's Law, which is a mathematical approach to gas solubility in water. So what happens to the solubility of the gas as we increase the partial pressure of it? As we increase the partial pressure of that gas, the solubility will increase. As we decrease the partial pressure of that gas, it will decrease. So the amount of gas dissolved, and we call that C sub G, is proportional to the partial pressure, the concentration of that gas above the solution. The more pressure of that gas, I like to think of it as the more pressure that gas is exerting, the more it forces its way, the more it pushes itself into a liquid. So that brings us to this thing called Henry's Law, which is the solubility of a gas is equal to K, something called the Henry's Law constant. It's different for any given gas at any given temperature, times the partial pressure of that gas. And notice that this is a linear relationship. So if you double the partial pressure of that gas, you're going to double the solubility. If you triple the partial pressure of that gas, you can put in 3 times as much, et cetera, et cetera. So now back to our soda analogy. With soda cans, you have a great deal of partial pressure of CO2 because it's sealed, it's in a small volume, a lot of that pressure of gas, so it's able to dissolve pretty readily into the water. Now, once you open it up, suddenly the volume that it can occupy increases a lot. So as a result, the partial pressure goes down and the gas starts escaping, and it keeps escaping. So imagine if you have a soda and it's opened and you have it sitting in a refrigerator versus sitting out on a hot day. Which one's going to go flat faster? The one sitting out on a hot day, more kinetic energy, it's easier for that gas to escape. And that concludes our talk about solubility and the like dissolves like rule. Thank you very much for your time and have an awesome day.